In this video, we're going to introduce a new and important probability distribution. Living in a remote rural village, Keith has noticed that his computer reports that the connection to the internet fails randomly, but at an average rate of 4.2 failures per 4-week period. What we want to try and do is suggest a possible probability model that will describe the number of internet failures during the next 5 days. So, first of all, let's try a very crude model. We'll start off by observing that the average failure rate is 4.2 failures in 28 days. So that's 0.15 failures per day, or if we like, it's 0.15 divided by 24, so 0.00625 failures per hour. So in 5 days, we would expect 5 times 0.15, which is 0.75 failures. So our first very crude probability model is simply going to say that there's a 0.75 chance of there being 1 failure and a 0.25 chance of there being no failures. That will certainly give us our expected failure rate of 0.75 failures over the course of the 5-day period. However, it's got one major assumption, and that major assumption that we're making is that there will be no more than 1 failure within the course of the 5 days. And that, of course, is a very major assumption, and it's unrealistic. So, we might try and improve that model somewhat. So, we know that the average failure rate is 0.15 failures per day, or 0.00625 failures per hour. What we could do is model the situation by splitting the 5-day period into 5 one-day periods. And for each of those one-day periods, say that there is a 0.15 chance of there being a failure and a 0.85 chance of there being no failures. So that will certainly ensure that I've got the expected 0.15 failures per day. And we can then say that x, the number of failures in 5 days, can be modelled by the binomial distribution with n equals 5, because we're considering 5 days, and p is 0.15 because we've got a probability of 0.15 of there being a failure in any particular day. Now, what assumptions do we need to create that model? Well, 2 assumptions principally: no more than 1 failure per day, and that the failures are occurring independently of each other. So there is the graph of the binomial 0.15 distribution. So that is the graph showing the probabilities and the number of failures for model 1. Now, if you remember earlier in our series of videos, we looked at the idea of the modelling cycle. And one of the important things that once we had a model that we were reasonably satisfied with was to compare that model with reality, think about the assumptions and the simplifications that we've made, and decide whether they were realistic or not. And the major one we're still slightly worried about is the fact that we've assumed there's no more than 1 failure per day. So what we're going to try and do is we're going to go round the modelling cycle again and try and get over that problem. So the way we're going to get over that problem is we're going to split the 5 days into 120 periods are each of 6 hours. So we've got 5 days is the same as 20 6-hour periods, and hence we know that the expected failure rate is 0.00625 failures per hour. In 6 hours we would expect 6 times 0.00625, in other words 0.0375 failures in each 6-hour period. So our improved model is going to say that the model of the number of failures in a 6-hour period is going to be 1 with probability 0.0375, and it's going to be 0 with probability 0.9625. And if that's the case, then we can model the number of failures in the 5-day period by saying that x is binomial with n equals 20, because we've got 20 6-hour periods, and the probability of a failure in any 6-hour period we're saying is 0.0375. Assumptions that we're making there, well, no more than 1 failure per 6-hour period. Well, we're certainly getting to the point where that's beginning to look fairly realistic, although I have known my computer, the internet on my computer, to fail more than once in a 6-hour period. And we're also expecting the failures to occur independently of each other. So let's have a look at this model. We've already commented on the assumptions, and the graph for model 2, the graph for the binomial n equals 20, p equals 0.0375 distribution is shown here. Again, we can think about our modelling cycle, compare this with reality again. But our first assumption is much better than it was in Model 1. It's still not quite ideal. The failures occurring independently of each other, one hopes they do. Whether that's actually the case or not, I don't know. So what we're going to do now is we're going to try and generalize what we did moving from Model 1 to Model 2. We're going to improve the model by splitting the 5 days into n periods, each of length 120 divided by n hours, and see what happens as n gets large. So let's see how that runs. So Model 3, split the 5-day period into n periods, each of length 120 over n hours. We know the failure rate is 0.00625 failures per hour. So in one period, we would expect 0.00625 times 120 over n, which is equal to 0.7 over n failures. And we're now going to model the situation by splitting the 5-day period into n periods, each of length 120 over n, model the number of failures in a particular period by saying there's a probability of 0.75 divided by n of there being 1 failure, and 1 minus 0.75 over n probability of there being no failures. So that the number of failures in 5 days can be modelled by a binomial distribution with n periods, and the probability of there being a failure in any given period is 0.75 over n. What assumptions are we now making? Well, no more than 1 failure in each period, and that the failures occur independently of each other. How realistic are these assumptions? Well, if n is large, the first assumption shouldn't be a problem, because if we take n to be a very large number, the length of time that we've got, 120 over n, is going to be very small. It will probably be smaller than the time that it takes to rectify the failure. And basically we're going to replace this assumption by simply saying that failures can only happen one at a time. And we're also got to continue to assume that the failures occur independently of each other. Now what we've got at the moment on the diagram, what we've got at the moment on the slide is a mini video showing what happens as we change the value of n. And the video starts off with n being equal to 5, which was exactly the case that we had in model 1. And let's see what happens if we do that. So here's the probability distribution in the case where n equals 1. It's now increased to 10, and you can see the probability distribution is changing slightly. We've now moved to n equals 20. And you can see that as n is increasing, the probability distribution seems to be approaching a limiting value. And that limiting value has now been put in green. So what we're saying here is that as n gets larger and larger, there's a limiting distribution. The rule for this limiting distribution can be shown to be the probability that x equals r is 0.75 to the power r divided by r factorial times by e to the minus 0.75. Now your teacher may decide to try and justify this limiting distribution and its format to you in class. But for the moment we're going to assume that that is the rule for this limiting distribution. So the limiting distribution was given by the probability x equals r is 0.75 to the power r over r factorial, e to the minus 0.75, for r equaling 0, 1, 2, 3, etc. Now a random variable y is said to have the Poisson distribution. Poisson was a French mathematician. So the random variable y is said to have the Poisson distribution with parameter lambda, where lambda is a positive number, if the probability that y equals r is lambda to the r over r factorial e to the minus lambda for r equals 0, 1, 2, 3 all the way along. Now what we just have been considering is internet failures occurring at a random but average rate of 4.2 failures per 4 weeks. We said that if x denotes the number of internet failures in 5 days, then the expected number of errors was 0.75. And we've seen through the different GeoGebra graphs and the different models that we had that it appears that the x has the Poisson distribution with lambda equals 0.75. And generalizing the example that we've looked at, and which we've used to motivate the initial definition of the Poisson distribution, we can see that the Poisson distribution can be used when x is the number of events that happen in a time t where the events occur randomly and independently of each other. Events occur one at a time, so you can't have 2 events occurring at the same instant. And that on average the events occur at a uniform rate. That is, the expected number of events in a given interval is k times the length of the interval. If we've got that, then the random variable x may be modelled by the Poisson distribution, where lambda equals k times t. Looking back at the example of the internet failures then, we need to assume that failures occurred at random and independently of each other. We took it as being reasonable to assume that failures occur one at a time. There may be two or more reasons why the internet failed, but it still counts as a single failure. Failures were known to be made at an average rate of 0.15 failures per day, and thus we could model X with the Poisson distribution with lambda equals 5 times by 0.15, in other words 0.75. That concludes our introduction to the Poisson distribution, and in the next video we shall see how to use it.